we continue the discussion of point groups, and in this video we will discuss what are called the centrosymmetric point groups. The centrosymmetric point groups. Centrosymmetric means point group containing inversion operation as one of the operations. Inversion operation, which as we know is designated as 1 bar. So, any point group which contains this inversion operation or 1 bar is a centrosymmetric point group. There are 11 such out of the 32 point groups. 11 point groups have this inversion operation, and we call them 11 centrosymmetric point groups. So, there are 11 centrosymmetric. So, let us see, we have actually already developed all the 32 point groups and their stereographic projections. So, we have already discussed these 11 centrosymmetric point groups also, but we were not identifying them as centrosymmetric at that point. So, we will now do that. If you remember, this 11 number also came in part 5. We summarized our development of 11 groups of proper rotations. So, there are 11 groups of proper rotations. Exactly the same number of centrosymmetric group is there, because if you add the center of inversion, if you add the inversion operation to any of these groups, then you will result in 11 centrosymmetric point groups. So, the 11 proper rotation groups, if you remember, there were monoaxial groups 1, 2, 3, 4 and 6. Then there were dihedral groups 2, 2, 2, 3, 2, 4, 2, 2 and 6, 2, 2. These have one principal axis like 2, 3, 4 and 6, and perpendicular to that there are two fold axes. And there were two cubic point groups 2, 3 and 4, 3, 2. So, our job now is to add a center of inversion to each of them and see what the resulting groups are. So, we do this exercise one by one. So, this is the stereogram of group 1. It has no symmetry. So, there is only one general position. Now, if we add a center of inversion to this stereogram, which I show by a small open circle in the center, then this general position will be inverted in this point. So, since this blue dot represents a point above the equatorial, by inversion I will go to a position below the equatorial, and also inversion is a type 2 operation. So, it will change handedness, which I represent by a red open circle. So, open circle to show that it is below the equatorial, and a red color to represent that it is of a changed handedness. So, we can say, so I could have left this in its original state and do this exercise here. So, as you saw, I added another point there, an inversion center in the middle, and this group, if you see, is nothing but a group 1 bar. It's a group 1 bar. So, the group 1 plus the inversion operation 1 bar gives you a group 1 bar, which is a centrosymmetric group. When I say plus 1, it has to be interpreted properly. You are not simply adding one operation 1 bar, because remember the group closure property, as soon as you add 1 bar, all products of 1 bar with other operations in the group also has to be added. This is trivial in this case because 1 has only one operation. So, 1 bar also really adds just one more operation, and the 1 bar group is a group of 2 operations. So, 1 has one operation 1, 1 bar has 2 operations 1 and 1 bar. So, in this case plus really looks like that as if I am just adding 1 bar, but soon you will see that you will be adding more operations. In fact, you will be adding as many operations as were there in the original group. So, the centrosymmetric group will have correspondingly twice the operation of the proper rotation group from which we are deriving it. So, let us say in this case 2. So, now I do the operation 2 plus 1 bar. So, if I add inversion operation to 2, I get a position below there with opposite handedness and a position below here with opposite handedness. This, as you can see now, since each point blue point above the equatorial point has a equatorial plane has a corresponding point below the equatorial plane with change in handedness, the equatorial plane itself becomes a mirror plane. So, the group which results now is actually 2 by m, and this has a center of inversion. So, this is sometimes shown by including a white dot in the two-fold. So, the two-fold axis has a center of inversion if the point group is 2 by m. And now you can see that the general positions, there are 4 general positions in 2 by m, whereas only 2 general positions were in the original group. So, 1 bar is not just adding what I said just now, that 1 bar is not just adding one operation, but in this case it has added 2 operations. So, 2 plus 2, 4 operations in group 4. Now, we do it for 3. We add a center of inversion, again center of inversion. If we add, we show it in the as a hole in this triangle. So, the 3-fold becomes 3 bar, and if we do it for the general positions, so these positions invert. So, you get 3 more new positions. The group, this one, if you recognize, you have already met these groups in the previous part. So, I am going quickly. So, 3 plus 1 bar, this group is nothing but 3 bar, the group 3 bar. With 4, if I add 1 bar operation, again I show it with a hole in the center of the 4-fold rotation axis, and I draw the corresponding inverted points. Each point gets inverted. So, if you see, in fact, this point is not getting inverted below the equatorial plane there, but it is getting inverted below the equatorial point on the opposite side. But then the opposite side point will get inverted here. So, in the end, every point will have a point below. So, the equatorial plane again becomes a mirror plane, just as it has happened before in the case of two-fold. So, here also we have 4 plus 1 bar, each 4 by m. In the case of 6-fold, I have these 6 points, 6 equivalent points corresponding to the 6-fold. An inversion again generates a position below each of these points, making, as you are now already quite familiar, making the equatorial plane a mirror plane. So, you have 6 plus 1 bar, 6 by m. Now, we come to the dihedral groups. Dihedral group 2, 2, 2 is shown here, and all I have to do here also in 6, since we have added a center of inversion, we can show it in the earlier presentations we were not means I was not being very careful and indicating the center of inversion, but there also it can be shown whenever the center of inversion is there, that can be added to the 4-fold, 6-fold or 2-fold axis. Now in 222, if we add inversion center, so you can see this point will be inverted there, but this point will also be inverted there, and correspondingly you will get points here and here. So again you can see that there are new mirrors which have come. For example, this plane becomes a mirror, this plane becomes a mirror, and the equatorial plane also becomes a mirror, because every point above is being reflected to a point below. So the resulting group is, as you should be able to recognize it by now, this is 222 plus 1 bar gives you MMM. This group is MMM. 3-2, so 3-2 will give us inversion. The inverted point comes there, there and there. So you can now see that you have inversion center here. So the question is, what is this resulting group? If you see carefully, by adding this inversion you have also added some vertical mirror planes, because these vertical mirror planes, oh sorry, see I started with a little bit incomplete group. So let me complete that. 3-2 would have already given me points, the 2-fold would have given me another points here. So my original 3-2 group itself was incomplete, so I was facing some difficulty here in after adding the center of inversion. Now I am completing the original group, so I had to add these 3 additional points satisfying these 2 folds, and since I have added the inversion center, so I will have to now add the corresponding inversion points also. So this will invert there, this will invert there, this will invert there. Now you can see that we have generated some additional vertical mirrors, because this point here and this point here, the red and blue points, both are above the equatorial plane, and but they are of different handedness. So there is a mirror which is going this way. So between the 2 folds you have the mirrors, and similarly you have a mirror going this way and a mirror going this way. So it's alternating 2 folds and mirrors in the stereogram, and a 3-fold with a center of inversion in the center. So this particular point group, which particular point group 3-2 plus 1 bar is what is known as 3 bar M, because you have 3 bar axis and the mirror planes are passing through the 3 bar axis. So although we started it with 3-2 and mirror planes were generated, in the designation we have taken mirror plane as the generator and talking it as 3 bar M, calling it 3 bar M. So if you have 3 bar and you would have passed a mirror through it, then also you will generate these two folds. This is how we generated this group initially in a previous video. So now let us do it with 4 2 2. So 4 2 2 group is here. All I have to do is to add the center of inversion. So I add a center of inversion. This will invert all the positions. So corresponding to the blue points. Now I will have red positions. Wherever there is blue point above, I get a red point below, and where there is blue point below, I get red point above. So the group is easy to complete, and you can see that this gives you 4 2 2 plus 1 bar is the equatorial plane also becomes mirror plane now. So if you note that, we should complete the stereographic symmetry elements. Equatorial plane becomes mirror. These vertical planes also become mirror, as you can see from the general position. So this is 4 by m mm. For 6 2 2, again my general position is not yet complete, so let me complete it first. 6 2 2, so the two folds will generate these positions. So I repeat that exercise here. So left one I am keeping as a reference of where we are starting, and the right one I am converting to where we go after the addition of a center of inversion. So add a center of inversion, convert the points. So you can see, like in the previous group, the equatorial plane becomes a mirror, and these vertical planes also becomes mirror. And you of course have mirrors in between also. So what you get finally is 6 2 2 plus 1 bar is 6 by m mm. Now the two cubic point groups, the first one 2 3, to add a center of inversion to these, we have to remember that if you just, let's go back and see what happened in the case of 2. So when the 2 was in the center, was a vertical two-fold, I added a center of inversion, so I generated a horizontal mirror plane. So this will always be the case. Whenever a two-fold is there and I add a center of inversion, a perpendicular mirror plane will come. So if I remember that and do that exercise for 2 3 here, so as soon as I add the center of inversion on this right figure, all the two folds will make the planes perpendicular to them as mirror planes. So the central two-fold, which is a vertical two-fold, makes this plane, the horizontal plane, the equatorial plane, as a mirror plane, and then the horizontal two-fold, this one for example, makes this vertical plane as a two-fold. This will make this plane, sorry, as a mirror plane, and these are the only two-fold. And you would also know that as you add the center of inversion to a three-fold axis, that becomes a 3-bar axis. So since these inclined three-fold axes are also passing through the center where you have put the center of inversion, these become 3-bar. So this group we have met before, so I give the name of it. So 2 3 plus a center of inversion, this group is called M3 bar, which is another cubic group. Finally, for 432, we have 4-fold, 3-fold and 2-fold distributed in the cubic orientation. And if I add a center of inversion in this case, then we have again 4-fold with a center of inversion also makes the planes perpendicular to it as mirror planes. So you get a mirror plane here for this 4-fold. For this 4-fold you get a mirror plane here, and for the central 2-fold the equatorial plane becomes a mirror plane. The 2 folds will also make the planes perpendicular to them as mirrors. So for this 2-fold, for example, the perpendicular plane is just this one, which I am currently drawing. And for this one, it's on the other side. So you get all these planes as mirror planes. This 2-fold will make this vertical plane as mirror, and then this 2-fold, which I had missed to draw previously, but we should have it in both the diagrams. You get these mirrors. So this is a diagram now very rich in symmetry. You can see it's a complete cubic group, and this is the M3 bar M. So 432 plus 1 bar gives you M3 bar M. So that completes the list of 11 centrosymmetric group. If I summarize what we have done, so 1 plus 1 bar gave us 1 bar, 2 plus 1 bar gave us 2 by M, 3 plus 1 bar gave us 3 bar, 4 plus 1 bar gave us 4 by M, 6 plus 1 bar gave us 6 by M. The dihedral groups, 2 plus 1 bar was MMM, 2 plus 1 bar was 3 bar M, 2 plus 1 bar was 4 by M MM, and 2 plus 1 bar was 6 by M MM. 3 plus 1 bar is M3 bar, and 2 plus 1 bar is M3 bar M. So that completes the 11 centrosymmetric group. You may ask if why we have not, why we are restricting ourselves only to the pure rotation group and adding a center of inversion. Why can't I take a group which is not centrosymmetric but is not a rotation group either? So for example, the group M. So let's do that. So if you take a group M, which is not a pure rotation group, that is, it is not a proper group, it is an improper group. And it also does not have a center. So, if I add a center to this, what will happen? So, let us do that. So, suppose the group M is represented by the mirror plane. You have a general position, the blue point, and because of the mirror that reflects below the equatorial in that red circle. So, this is the group M. If I add a center of inversion, this plus 1 bar, then you can see that if you add a center of inversion there, then again on the other side you will generate a red circle and a blue dot. So, this is the group which we called as 2 by M, because it has a two-fold and it has an inversion center. So, M plus 1 bar is also 2 by M, which came to us from the operation 2 plus 1 bar. So, in the remaining groups which are neither proper nor centrosymmetric, if you add a center of inversion, again you will end up with one of these 11 groups. So, this is a complete list of 11 centrosymmetric point groups. Thank you very much.